Thank you, Jonty, for taking your time out to actually have a chat with you about who you are and, of course, your upcoming public talk. So, Dr. Jonty Marshall, can you tell me a bit about yourself and how you got here at UNSW Australia?
Yeah, sure. Okay, so I started my research career way back in 2000 when I went to university at St Andrews in Scotland, in the UK. I did undergraduate degree in astrophysics there. Then I moved on to UCL in London to go and do a postgraduate master's. From then, I moved to Milton Keynes to do a PhD, working on the detection and analysis of debris discs, which are remnants of planet formation, which is what I'll be talking about
in the talk. The debris discs.
Exactly.
Cool. Excellent.
And then I was involved with a couple of research groups there, international consortia, that were working on a space telescope called Herschel. It's Herschel Space Observatory, which is an ESA-funded mission with contributions from NASA, which was designed to look at the all sky in the far infrared. So looking at basically the cold emission from the universe, so dust and gas that's sort of not in stars, it's kind of in the interstellar medium or at high redshift or kind of all the circumstellar material, the dust that I look at.
Yep.
And so therefore I got involved with a couple of those guys, and one of them was looking for a person to produce all their data for them, data analysis expert. Yeah. So I'd worked on some other data during my PhD for another survey that hadn't quite panned out in terms of its results. But the one I was working with the Herschel Space Telescope was working really well. So I got signed up to their consortium and moved up to Madrid to go and work with the PI and work on the data reduction for their survey.
When you say PI?
The principal investigator,
okay.
the boss.
Yeah,
the boss.
Research
El
yes.
Capo, El Jefe, I'm the boss of the bosses.
Yeah.
So yeah, I went to work out with him there and sort of ended up after sort of a couple of years, sticking out there for another couple of years. And then, so that was back in March of this year, I finally moved on from Madrid to come out to UNSW in Australia to be a Vice Chancellor's postdoctoral research fellow.
Well, congratulations on that.
So thank you. Happy to be here. And it's, so I've now sort of taken the work I did with my PhD on debris discs and then the research I did working with the Dunes Consortium with Herschel data, the dust around nearby stars.
Oh, right, okay.
So it's kind of, there's another one called debris, which is disk emission via bias-free reconnaissance in the infrared and sub-millimeter.
These acronyms.
We had a better acronym.
Oh, right.
Yeah. Seriously, can you try to say that after 3 points? Not going to happen.
You can't is Herschel, or is that an acronym for something?
No, it's named after William Herschel, which shouldn't be confused with the William Herschel telescope on the Palmer.
Okay.
So there's two William Herschel, there's two Herschel telescopes. One of them's William Herschel, which is in Palmer, and the other one's the Herschel Space Observatory, which is
the stuff that you work.
Is the one I was working on. Yeah.
Why did you choose the name Herschel? Of course, rather than being a pioneer in astronomy, what specifically did Herschel do to inspire the name of this telescope?
Yeah, Herschel discovered the infrared emission, and by his experiment where he took a prism, scattered the light from a prism onto his desk, looked at the colours, and then stuck a thermometer, apparently, it depended on who you believe, it's either just stuck a thermometer there to check if there was anything out there, because the desk was warm where the light was, and then, or he just left it there by accident and then saw that the temperature was warmer off the end of the spectrum. And therefore he identified that there was something there that was causing it to be warm, and this infrared emission, i.e. beyond red emission.
So the light was coming from where, sorry?
The light was from the sun. So it was just sunlight. He just scattered the spectrum of sunlight. And
I always thought the optical wavebands will actually give off more energy than the infrared. So why did it give off more temperature?
Because effectively the temperature you feel is just light at a very long wavelength that you can't see.
Yeah.
So at optical wavelengths, we see blue, red, green. Or blue, green, red if you want to do it in order. Yep. I'm a scientist, really.
It's okay, it's just colours, right?
And then, colours are relevant. And it's in that spectrum, that region of the electromagnetic spectrum, as we call it, which spans from X-rays up to radio wavelengths, in that little bit that we can actually ourselves detect as people, there's just the optical, so covering blue to red. Yep. Now, if you go beyond that in either direction, there's still light there. Things still emit. Because that's the way the world works. Yeah. And there's part of the infrared emission is this effectively longer wavelengths than we can see in the visible, from beyond the visible. And that expands out to kind of, longer wavelengths, colder temperatures. So, and that's something to do with it's called the blackbody radiation, which is an approximation whereby if you have an object of a temperature, it will emit as a characteristic function of its wavelength.
Yes.
And therefore, if you know what it looks, how much light or how much energy it's emitting at different wavelengths, you can then tell what temperature it is just by fitting this Planck curve, it's called blackbody curve, to the observed emission. Yep. And so at stars they emit, conveniently enough, mostly in the optical.
Yes.
Which is
makes sense.
Exactly. We see in the optical. They emit in the optical. It just turned out nicely. Yeah. I mean, whereas the stuff that I look at, the dust and the debris discs that I look at, they mostly emit in what's known as the far infrared, which is wavelengths which are sort of beyond kind of 40 microns-ish. Now, when I say a micron, visible light, so the sort of yellowy white light we see from the sun, that peaks at about half a micron. Okay. And what you use to heat up your tea in the microwave, that's about 1 millimeter-ish. So that's like 1,000 microns.
That tiny. Yeah, it's
like teeny tiny. But really big as far as wavelength.
Yeah, but far infrared is even.
Far infrared is kind of in the middle between those two. So it's bracketed. So it's about, most of the work I look at is with sort of emission about 100 microns or so. So it's about 200 times longer than optical and kind of 10th of the length that your microwave operates at. Yeah. So it's kind of smack bang in the middle. Yeah. Although that's where most of my focus of my work is, but I do sort of combine measurements from kind of all sorts of different places, because of course what I'm looking at is dust around stars. Yep. And therefore, in order to be able to characterize this properly, you need to be able to understand what the star's doing, which mostly emits in the optical and near-infrared, and you also need to understand what the dust is doing, which emits in the sort of mid-infrared, far-infrared, and what's known as the millimeter and sub-millimeter. So very long wavelengths. Yeah.
So can you take me through the process of the current idea of how planets actually formed around stars?
Yeah, sure. Okay. In the beginning, you have a molecular cloud, and in that cloud there are slightly overdense regions, which are cloud cores. These are about 1/10 of a parsec across, where a parsec is a parsec is 3 and a bit light years, so 3.26 light years.
So light years.
A light years isn't the light travels in a year. Yep. So they're quite big, and they're not very dense, and they're very cold. They're sort of temperature of 10 Kelvin, so water freezes at 273 Kelvin. So 10 Kelvin is very, very cold. So 10 to 20 Kelvin is the temperature of these objects.
And where 0 Kelvin is sort of...
0 Kelvin is absolute zero, and you can't go lower than that, at least as far as we know.
Yeah.
I've got to hedge my bets for the future. This is going to be on YouTube. I need to hedge my bets. Exactly. Yeah. So these things are very, very cold. And the idea is that these cloud cores are triggered to collapse. So they become gravitationally bound and they collapse down. So you get this large amount of material in a very diffuse kind of cloud core. But it's sort of about solar mass, of course, in sort of
solar mass meaning
being the mass of the sun. Yeah. Mass of the sun, and it sort of collapses down into this kind of object that goes from being this 10th of the parsec size to being a few thousand AU in size, where an AU is an astronomical unit, which is the mean distance between the Earth and the sun. Yep. And these things sort of collapse down, and as they collapse, if there's a slight rotation to the cloud core, because of angular momentum, the cloud will go from being a big sort of amorphous clump to being kind of a disc shape. Yeah. Now, at this point, you get the protostar forming in the middle as a gravitationally bound object, and you get this big sort of disk all around it. And the material that goes on to form the star has to be funneled through this disk, which is kind of lots of gas in it, lots of dust in it from the material that formed in the interstellar medium. Although existed in the interstellar medium, sorry, should I say. And inside this disk, this sort of circumstellar disk, as the central object forms, there is also planet formation going on. This is called a protoplanetary disk. So the dust that's in that circumstellar disk basically grows by collisions, and it sort of settles into the midplane of the disk. So you get a greater density of material, solid material. This solid dust is grown up and goes from sort of dust grains at kind of a tenth of a micron, half a micron size.
Very tiny.
Very, very small, very, very small. Up to kind of sort of micron-sized particles, then going on to sort of millimeter-sized pebbles and boulders, and then eventually you kind of get up to the stage where you've got kind of what we call planetesimals, but these are kind of like stuff like the asteroids and comets in the solar system. You get large kind of kilometer-sized, so it's 100 kilometer-sized bodies, and these are the building blocks of planets. And these exist inside the gassy disk as it evolves around the protostar. And eventually gravity takes over, and these things collide, and they grow up into a protoplanet. Now, that can be the end of the story, and you get just a rocky planet. Or if the rocky body grows large enough, it has its own gravity that it can pull material off the disk onto its own atmosphere.
Hence you got the outer gas.
So then you get gas giants, and you get sort of two types of planets. You get three types of planets. You get little rocky terrestrial worlds like the Earth and Venus. You get your big gas giants like Jupiter and Saturn, and you get in between that, you get your ice giants, which are things like Uranus and Neptune, which are kind of didn't have quite a large core, but they didn't have quite enough time or material left to pull off a significant gas envelope. So these sort of planetary, the sort of spectrum of planetary types we see is kind of a reflection of their formation process, which is in turn a reflection of the material that the star itself, the protostellar cloud, the star itself eventually formed from. So what I do is I look at the material that's left over once the planet formation process has stopped.
So you don't actually directly observe these dust grains?
Oh, you do. This is the thing. You do observe dust grains
because I thought they'll be so tiny that you.
The great thing. That's the great thing. Right? That's why we can see them, because if you've got dust,
yep.
and if you grind something up very small, it's got a very large surface area.
Oh, okay.
And the amount of emission you get from something is dictated by its surface area. So if you've got a large surface area, you'll be able to see it more easily.
So you're looking at the bulk material.
We're looking at what we do is we look at the bulk material, these dust grains that comprise part of the distribution of bodies that exist in these circumstellar disks. Yes, whilst we see the dust grains, the important thing to know is that there are like larger bodies going all the way up to kind of these asteroids and comets. So whilst the majority of the mass in these circumstellar disks we see is in these very large bodies, what we actually observe is just the dust grains that are produced when these larger bodies collide and disintegrate a bit.
Okay.
And the reason we know that these dust grains are produced by the very larger bodies, and these large bodies must exist, is because the dust grains themselves are removed either by collisions or by being picked up and taken away by the starlight from the system on very short timescales. And the systems I look at are very old, and therefore they're much older than the lifetime of the dust grains. So therefore they have to be continually replenished in order to actually be able to see the disk as we see it at the current time.
Yeah. Wow, a lot involved there.
Yeah, a lot to think about.
Yes. So you would regard yourself as an observational astronomer then, looking at optical data? So you're looking at surveys of data you actually mentioned. So you're looking at not one star with a protoplanetary disk, but multiple systems? Yeah,
the Dust Around Nearby Stars, the June survey that I was involved in, that looked at a...
June is another acronym, is it?
Dunes, yes, Dust Around Nearby Stars.
Oh, right.
Dunes,
okay.
yes.
Okay. Dunes, okay, fair enough.
That survey was looking at 133 stars, with plus a few others from another survey which we had some joint observations with. That's probably a detail we need to talk about. But we had a sample of 133 stars, which comprised most of the what we call sun-like stars in the solar neighbourhood. Now, sun-like stars are stars kind of either slightly more massive down to slightly less massive than our own sun, and they have therefore they have similar properties. And they've been a favourite target for exoplanet searches.
Oh, okay.
And we're looking at them not for the exoplanets. In our case, we were looking at them to see if they had any dust around them. Because part of my research and what I do is linking the stellar properties, the presence of a planetary system, and the presence of a debris disk, so a remnant from a planet formation process.
Oh, okay.
And in that case, I'm trying to link these kind of three sort of fundamental components of planetary systems together into a kind of coherent picture of the the outcomes of planet formation, basically.
Oh wow! So you're just filling in the gaps of
Yeah.
that process you just described.
Yeah.
That whole overall thing.
Yeah, so I'm trying to work out what we see, if the planetary systems we see around other stars are typical, shall we say,
Yeah.
are what we would expect, and therefore what implications this has in terms of the presence of planetary systems like our own, and in the longer term, discussing sort of the habitability of the planets we see around other stars. And where the material that I'm not going to talk about ice and volatiles delivery. I'm not going to talk about that.
So you'd be talking about this in your upcoming talk?
Yes, no, I will talk about sort of how these planetary systems form,
Yep.
how we deduce that there is actually a planet formation process having undertaken around those stars, and detecting the remnants of that planet formation process through this remnant debris, this dusty circumstellar disk, and then talking a little bit about how we link the planetary systems we see with the debris belts we observe, and how that relates to the stellar parameters of the host star.
So you have to come up with a model to confirm these observations, I guess.
Yeah, whilst I'm much more of an observer, I collaborate with people who do a lot more of the modelling side of things, and they work on theory.
Jonty Horner.
Yeah,
because he talked a lot about his modelling technique and actually confirming whether these planetary systems are indeed systems as well. So do you work with Jonty? I mean, do you work closely together in getting these ideas confirmed?
Yeah, we've produced a few papers together, and worked a bit on the dynamic side of things in terms of looking at the stability of these planetary systems and how debris belts and planets interact with each other through their mutual gravitation. In addition to that, in terms of looking at the stability and the dynamics and the evolution of these objects as a kind of a clockwork system. I also look at, with other modelers, I've looked at the thermal emission and modelling that, and so looking at the light we see given off at the infrared wavelengths, and then trying to do something about the properties of the dust grains that would have emitted that light originally. And I work with a few groups in Europe on that particular problem, and trying to see if by taking a picture of the disk, and so knowing from the image where the dust is around the star, then relating that to the models we have of the emission and what we'd expect to infer just from the models of the emission, and then sort of combining those two together and saying, well, how does this change our view of what the dust is actually made of, and what the dust properties are? Once we know where we're looking, how does that influence our modelling, and then sort of a cyclical approach, iterating down to derive the best physical properties for these
So you're
systems.
taking observations to change the model rather than trying to change, well, it's sort of approaching it scientifically as best you can.
I like to think I approach things scientifically as best I can. Yeah. My collaborators may have different opinions.
Yeah, but it's good actually. Are you eliminating sort of ideas of what it could be? So we're testing one idea and go, well, it's not that. Keep on eliminating that way? Or? Yeah,
and certainly it's more a case of opening up the possibilities at the moment rather than eliminating possibilities.
So it's a discovery mission.
It's certainly more of a discovery space at the moment. I mean, we do eliminate possibilities in terms of, well, the dust can't exist there, and the dust can't be made of this particular material because it wouldn't look like this if it did. But in terms of opening up discovery space, we're sort of looking at what the composition could be in terms of when we look at astronomical dust, we sort of assume it's kind of a rocky, it's sort of dirty snowball type thing, sort of a mixture of like kind of rock and ice and just slammed together. And what we can kind of look at, if we can get enough detail, we can sort of look at it and go, well, can we say there's water ice in there? Okay. Can we say what kind of silica, if there's kind of, what kind of rocky material is there in there? Is there kind of, can we even say, is there kind of like kind of dirty kind of carbon type material, like soot? Is there any of that in there? What kind of material components can we sort of stick into our kind of dirty snowball and make it match the observed emission?
Okay, so how do you ascertain what type of material you use? Are you taking images, or is there another technique that you're using?
We use spectra. So this is kind of in the mid-infrared. So wavelengths around kind of 10 to 30 microns, basically. And there's some interesting emission features there from material components that we expect to see in the debris dust around other stars, because we've got measurements from our own solar system. So, because our own solar system is a debris disk host star. It's got your 4 inner planets, you've got the 4 outer planets, and you've got 2 debris belts. You've got the asteroid belt, and you've got the Edgeworth-Kuiper belt.
Yep.
And so, looking at the meteorites that fall to Earth, and then you've got in situ measurements with dust impact missions that are travelling through out to the outer solar system now, and looking at the emission from sort of asteroid surface measurements, or for example the Deep Impact mission, which threw a copper slug into an asteroid and sort of kicked up a whole big cloud of dust, and they took a measurement of what that dust was made of.
Yep.
And from these various measurements in the solar system, where we can get a really good and really close look at what the material is made of, we can kind of say, well, we kind of expect to see stuff around other stars made from the same material. And it's a good approximation. It's a good first guess.
Using our solar system.
Exactly. Using our solar system as a point of reference, as a model, we then take the material components and go, let's have a look at the emission we get from other stars, around other stars, and then see if it matches up with anything we can see in our solar system. And yeah, sometimes you sort of see sort of more cometary-like dust emission, and sometimes you see kind of asteroid-like dust emission, and sometimes it's a mixture of the two. And so yeah, it's very much a kind of taking something you know and understand, and then kind of looking at something you don't understand and saying, does it look
about right?
Is it about right?
It's actually matching spectra.
Yeah, there's a lot of like transparencies and kind of moving things up and down and left and right and things.
It's not quite like that, is it?
It's not quite like, it's mostly done on the computer, but it's...
okay.
I mean, there's a lot
you
of...
spend most of your time in front of a computer, I take.
Sadly, yes. Yeah, unfortunately, no, I much so would love to have gone and spent some time up at the observatories. Unfortunately, the trips to space aren't...
not on the card.
Not on the card, sadly NASA won't stump up for me.
Yeah,
I keep asking, but they keep
the
saying no.
You do work indirectly for NASA in a sense, because the Herschel instrument is a NASA space telescope.
It's just NASA is responsible for part of it, and so yeah, I do work with people who are actually at NASA.
Oh, right.
So
that's pretty cool.
I kind of might be able to claim I'm sort of an astronaut by kind of 3 steps removed, maybe.
Oh, right.
Which is probably a huge stretch, but I'm going to claim it anyway.
Yeah. So, getting back to Earth in a sense, you mentioned astronaut. As kids growing up, people look up to astronaut and be inspired to be an astronaut, but they don't end up being an astronaut. But you've actually was inspired to become an astronomer. So, was there a spark? Can you take us through that? Or?
Yeah. Okay. It's not a very worthy story, unfortunately. I was inspired by far too much trashy sci-fi as a young child. I watched all the Babylon 5, the Blake 7, the Star Trek, all of those, and that got me interested in space as a concept, and certainly as astronomy. And that was kind of encouraged by having my parents kind of got me kind of like planispheres and telescopes and kind of like little kind of kaleidoscope constellation viewers and things. So I was kind of encouraged down a kind of sciencey route. And certainly astronomy was what really sparked my interest in that regard. And then moving on to that, at school, I had a really good physics teacher, Mrs. Mead. So she inspired me at my A-levels to basically take up physics, at least, at university. And then once I got to St Andrews, I suddenly discovered that astronomy was a damn sight more fun than actual physics. And so I was like, yeah, I'm going to do astronomy. I knew once I got to university, I was like, yep, let's do astronomy, and then carry on from there. And I've never looked back, really.
Awesome. So science fiction.
There's been a bit of a geek revolution recently. And I don't know what prompted it, but certainly, yeah, science topics and sort of technical. I think certainly in terms of looking at people interacting with technology, not even through science, perhaps through engineering or through programming, people have really kind of come to believe that's a good thing and that's something to be encouraged. And so, yeah, there's kind of this kind of movement towards.
Do you think it's like the onset of the internet, more sort of access to information around the place that will contribute in there?
I think so. I think it's sort of comparable perhaps to when people first got into computers back in the 80s, where you had sort of sitting in your bedroom and sort of building your computer from scratch with a soldering iron and then sort of writing your own games on the computer. Yes. And it's sort of getting into that stage again where people are sort of feeling they want to actually interact with their technology on a personal level somehow. And so that's something that should be encouraged for sure. Yeah.
Well, in terms of social stuff, you are giving a talk on Friday, June 20th on Cicrumstellar Debris Discs. So essentially your research, and hopefully it's going to be explained to to everybody. So hopefully not too much technical jargon. So.
I'll try to cut down on that. Sorry.
No, it should be fun. It should be a good talk. Finding out where, how planets are formed and where we actually come from, I guess, in a sense. So thank you very much, Dr. Jonty Marshall, for taking your time here to have a chat on a Thursday morning and with no coffee either. So that's pretty impressive.
Thank you for having me without coffee.
Thank you. Cool.